Okay. Okay. Good morning. Last class, we studied the post-stratification. So post-stratification in subway sampling and post-stratification in on the completely randomized experiment. And so the key part is that the point estimator has the same form as the stratified sampling estimator, but the only difference is that the sample size in the denominator is random. So we need to apply the linearization. So if you apply the linearization here, right? So if you apply the linearization here, then you get this part, and then which can be simplified as something like this. So so that's what we obtained. I mean, we derived last class. So this is what we have. And then, and if you want to compute the variance, so then we use so how to compute the variance. So this is essentially the variance on the so apply the variance formula on the completely randomized experiment. And so we in the completely randomized experiment, our estimator here uses yi, but now we have a ei, which is actually kind of a residual error term from the regression of y on the straight mean. So then, so originally, right? Originally, the okay, what is let me. So variance of tau hat time in the original okay ti yi plus 1 minus ti yi. Oops. Right. So no, it says should be minus, right? Sorry. Okay. N1 ti yi minus N0. So this is the point estimator time on the completely randomized experiment, and then variance of time is what is 1 over n1 minus 1 over n s1 square plus 1 over n0 minus 1 over n s0 square minus 2 covariance, right? Let me try to see where we get this formula before. I think we get this in chapter week 3, I guess, right? No, week 2. Okay. I'm sorry. Second part of what? Week 2. Okay, thank you. So let's go back to our check. Okay. So yeah, let's check. This is simple random sampling. And so maybe week 3, part 1, I guess. Yeah. So we basically this one. So which is essentially I think we have this. So right. So this is okay. So let me yeah. So right, the covariance between the two is minus one over S01. So then we have a minus times minus is plus. So plus. But that is the that is the formula. Okay. And now this is complete randomized experiment. But now our estimator here, right? Tau here post distribution is a tau plus same thing, but the only difference is that we have a different minus pi pi 0. So the variance should be the very so when it comes to computing this one, here this one is 1 over n1, for example. Sorry, n minus 1 I go to 1 to n yi 1 minus y bar 1, something like that, right? So here we have this guy, but now we use ei rather than yi. So that is the main difference. So then the variance should be, so the first part should be the same, but then this guy is indeed something like ei 1 minus e1 bar, right? Plus 0 plus 2 1 over n so that's the same formula using ei instead of yi. And then you can see that so for example, what is this? What is this? So this guy using this definition, right? Using this definition is yi 1 minus y h bar 1. But this h is a mean, right? Straight on mean. So that means you cannot really write this way. So you actually need to partition the population into two parts. Double summation, h equal to 1 to h, I equal to UH. Okay. So once you do that, and then this guy should be 0 because this is the overall mean, but this is mean adjusted by the straight mean, right? Then if you take the summation over, then this will be 0. Summation over h will be 0. So then overall it should be 0 too. So then you have this one. So that means you can get write something like h and then WH times SH1 square, roughly. So basically, this is kind of within some scale, right? This is a within. And so the within is actually can be written as something like this. Right? So so that's how you get this part. So you get this. So this guy, right? This guy. So this guy is just 1 over n1 minus n1 n, right? And then this guy comes from here. By the way, this is not exactly so. So actually, if I should include this one too. Okay. Shouldn't divide. Sorry, I shouldn't. So this is maybe I should write it a little bit clearly. This guy is 1 over n, of course. And then because this is subscale within divided by n, and then this is a so that this one is actually s squared. I mean, this can be written as a weighted sum, weighted average of the within variances, right? So that basically gives you proves the first part. Second part should be the same, right? So second part multiply 1 over n is 1 over n0 over 1 over n times this guy. Oh, sorry, this is a typo. It should be 0. Okay, so should be 0. Because this is a variance about E1, and this is should be the variance about for corresponding to E0, right? And then this one is covariance to E0 and E1. So that is the how you get this. Okay. So that's all about post-stratification. Now let's move on to another topic, new topic in week 5. Okay. So ratio estimation. So now we are moving back to a survey sampling. So Horvitz-Thompson estimator is design unbiased, right? But we didn't really say that Horvitz-Thompson estimator is efficient. I mean, small variance. We don't care. I mean, could be actually inefficient, very inefficient. And then maybe the important question is how to find the minimum variance unbiased estimator on the survey sampling, right? This is pretty much a very standard problem in statistics. So, okay. So here's the formulation of the problem. So suppose I have a parameter defined, the finite population parameter defined as a function of the finite population element, right? And then suppose, so this is definition, right? So on estimator, which is a function of, right, a function of y's in A, in the sample, it can be called UMBE if it satisfies two conditions. First, it should be unbiased, right? It should be unbiased. That means it is the expectation of the estimator under the sampling design. So this means the notation here means that it's not really about the y distribution y. We don't treat the y as a random variable, right? Y's are fixed. So the notation here means that the expectation is a function of y's in the population. Okay, because you take the expectation, right? If you take the expectation with respect to the sampling design, so under the sampling design, it will be a function of y values, right? So in that sense, this we have a substitute y. The right side is also a function of y. So as an equation for y, this should hold as an identity. Okay, so that means for all y. So that is unbiasedness. And second condition is that it should be so the minimum variance. It should be the variance should be less, right? No greater than the variance of other unbiased estimates, right? So second part is a minimum variance condition. So the variance should be less than or equal to the variance of any for all unbiased estimator for all y. And here the uniform. What do you mean by uniform? Uniform means for all values of y, right? So in general, so if you, for example, in the mathematical statistics, on estimator is unbiased uniform minimum variance unbiased estimator means what? Expectation theta equal to theta, right? And then variance of theta hat. So theta hat star. Same thing, right? For all unbiased estimator of theta hat of theta. So that is the, stat. I don't know whether you learned this, probably step 543, right? 543 thing, right? So in 543, you should learn this kind of thing. But the important thing is what I mean by uniform. Uniform means for all theta. So that means this relationship as a function of theta, right? As a function of theta holds for all theta. So theta here, but theta here means in our context is in all population. So here is a trivial example, kind of a trivial example. So suppose my estimator is 12, no matter what, okay? Then under the particular parameters, right? Under the particular parameter, which happen to be 12, then this is unbiased for that parameter, right? For that particular model. And the variance is 0 because this is a constant. But this is nonsense, right? You completely ignore the data and give the same value no matter what. That's totally nonsense. So that means we want to exclude this kind of weird estimator from our consideration, right? So that's why we want to include impose uniform condition So here is Basu is a uh gave a very interesting result. So basically, in survey sampling, no UMV exists. So, so that's what the theory says. So how, okay. Suppose, so how can, so now how to prove it? Well, how to prove non-existence usually? Then usual technique is to assume there exists a UMV and show that it has some contradiction. Okay, so that's the usual idea. So suppose you have a UMV. Okay, so say Q. So given and then and for fix any value. So this is a particular vector of population vector. And then you construct this estimate. So you construct this estimator. This new estimator is unbiased. Why? Expectation of Q star A is expectation of. So Horvitz-Thompson estimator of this one is what? Summation I k equal to U yk minus k star plus no U, maybe 1 to k. Okay. So this guy is indeed unbiased for the total, right? So that is unbiased. Second part is interesting. If the finite population that we happen to be exactly equal to this number, okay? If finite population happen to have this to be exactly this number, then what? Then then if you plug in, so in this case, your estimator, right? Your estimator for this particular value of population is equal to this guy. So that means it is actually zero variance. Okay. So this estimator is always unbiased. And if so unbiased for all y star. I mean for all y. Right? But the second part is that it is a smallest variance if for this particular y. And now, if so, this is one estimator, but we start with assuming that there exists a UMB. So then the UMB is supposed to be better than this estimator, and which is impossible because this is zero. So this one is this one is unbiased for one value of population, and you can construct another estimator which is also so basically this guy is zero for this particular value. Now that means which means that because of the definition, this is zero. Oh, sorry. Uh, so this is zero, right? Because this is This is 0, right? So this is 0. The right side is 0. So that means this has to be 0. But we can change this y star arbitrarily. That means this q hat will have 0 values for y, which is impossible. So UMV cannot exist. Okay. Okay. So that is the kind of shocking result in the history of survey sampling. And then so that means the class of design unbiased estimator is too big. So this is too big, so we cannot really find the best one. So maybe we should choose consider a smaller class. And if you narrow down, choose your class to be linear estimator. Okay. Then we also have a problem because so this class is too big. So there's no best uniformly best one. So okay. So then how about this class? This class is a small class. Turns out that this class contains only one element, which is a Hurwitz-Thompson estimator. Why? Because if you think about that, what is this? Wi pi I yi. So we want this to be equal to yi for all y. Right? So we want this to be equal to, because if you treat wi as fixed, then the expectation is just the expectation over the indicator, which is pi I. So then this equality implies that, so this implies that pi I wi equal to 1 for all I, which implies that wi equal to 1 over pi I, which means that weight has to be 1 over pi, which is a Hurwitz-Thompson estimate. So then that means Hurwitz-Thompson estimator is the only unbiased estimator among this class of linear estimator. So this is not really interesting, right? Because what's the point of considering optimality in a set with a single element? No point. So this one is too small. This one is too big. So we should have figured out a reasonable class, right? Somewhere in the middle that gives us some interesting idea. So the answer is, here's the alternative definition of linear. So it is linear in Y, but the weight can be random variable. That is really, really important. So weight depends on the sample. So weight can be random, not fixed. If you treat weight as fixed, then you have no freedom. So you have to have some flexibility in the sense that weight can depend on Y. No, weight can depend on sample A. So that's why we have a subscript A. And this linear estimator is actually quite attractive because of the this property, internal consistency. So what do I mean by internal consistency? Because if this is linear, right, then your estimator applied to, suppose you construct the Y3 from Y1 and Y2. So if you think about Excel file, you have a column column represent the particular score, for example, right? So your score in the midterm, your score in the final, and then your total score, right? So then we should make it consistent, right? Your sum total in the middle score, the total sum of the students in the midterm exam plus total scores in the final exam should be equal to the total score of plus sum of the midterm and final, right? So that's important, right? So if we have this form, then we have this equality, right? But if weight, so what it would be the example of where this internal consistency does not hold? Where if your weight is a function of y, so if your weight depends on y, then you don't have this equality, right? So then it's very weird estimator, right? If this one does not, this kind of property does not hold, then people will, I mean, the practitioners will hate it because it's every time you have to. So you can construct estimator and you can construct estimator, but you cannot really add these two to obtain this, right? You have to do something else. So that's not really attractive. Okay. Okay. So anyway, that is the I think there's a notation is not really consistent. Okay. So let's move on. Ratio estimator. So let's recall the toy example that I introduced in the beginning of this semester. So we have a farm, right? Farm. This is a farm toy example. So now average farm size is known. So that means what is so 12, so 6 and 36, right? 36 divided by 4. Okay, 9. So average is 9. If you simplify the sampling of size and 2 and end up with so you apply simply the sampling and you happen to obtain the smallest 2 small farms. Okay. So then what is the average? 5. Okay. So I know that average is 9. Population average is 9. But my sample has a sample average shows 5. Okay. What should we do? Right? Well, that means I know from this value, I compare these values, I know that my sample happen to be small ones, right? So that means the average yield. So the average is 2. Average should probably underestimate the truth, right? The sample average must be underestimating the true yield in the population. So one idea is, okay, then I know that this is 9 divided by 5, right? So the sample underestimate X bar by a factor of 5/9. So then I want to recover it by applying the ratio, which is multiplying 9/5. Then if I apply to x mean of x is 5. So then I recover 9, right? So then this 1.8 to the sample mean. So that means for each choice, right? My y bar is originally 2, but I multiply 1.8. 1.8. And then this one is what? 1, 3. 1 and 3. So then average 4 and 5. I have 4 and 6, which is 5. So that means my factor is 1.82. But what about 1.1 and 4? 1 and 4. Now I happen to select the smallest one and the biggest one. So then average is 20. So 24 divided by 2, which is 12. So sample mean is 12. But the population mean is 9. So that means this is the sample mean is bigger, greater than the population mean. So that means what? I should probably apply, multiply this. 9 divided by 12. So again, population mean and denominator sample mean. Okay. So which is actually 6. So you can see that the factor, right? The sample mean is just obtained from the sample, but this factor, adjustment factor changes with your sample using x values. Okay, and then so now let's take a look at the property. So for example, let me so 3 and 4. 3 and 4 mean is 13, right? Mean of x is 13. But population mean is 9. So I know that I happen to select the oversample the bigger one. So it's better to downweight this way. Okay. So that basically is the idea. So ratio estimator is really a popular method. And then the first thing you can see is that it's not unbiased. It's actually biased. So that's different from simple random sampling, right? I mean the sample mean. Sample mean is unbiased, right? Sample mean is unbiased, but maybe higher variance. But ratio. So if you look at the distribution of the two values, right? So distribution is 2. Okay, maybe this is better. So you have a 6, right? You have 6, and then 6 is the mean, but your point, you have a 8 point, 6.2, 3, 4, 8, 9, 10. So that is a sample mean, the distribution sample mean. While this guy, the smallest one is a 3.6 here. And then 5.4, so which is here, 6 and 6 and 6.23 and 6.9. So these are the distribution of the ratio estimate. Right? So you can see that the variation is much smaller. So you can see that the variance will be small, right? So which is exactly what it shows here. So variance of the ratio estimator is 1.9, 1.0 something, while the variance on the simple random sampling, the mean is 9.6, so which is much bigger. So even though the ratio estimator is biased, right? The ratio estimator biased, the mean square error is actually much smaller. Okay, mean square error is much smaller. than the that of the sample mean. So then that means why not, right? Why not use it, right? It's a good idea to use it, even though it may have a bias, but maybe it's in terms of the mean square error, it's just a little bit small anyway. Okay, so that is the kind of uh, toy example, simple toy example that illustrate the idea for ratio estimator. So, so the ratio estimator is applicable for scalar. When we have a scalar auxiliary variable, usually positive. I mean, in most of the survey items that we in practice has positive values, right? Crop acres, income. I mean, some people may have a negative income, but usually say we have why will it be positive, right? And then it makes sense to use positive x too, right? And maybe positively correlated with the study base. So one kind of presumption is that x has to be a good predictor for y, some sense. And one important assumption is that we should know the population mean or total of x from external source, not from the sample. So when you say external source, means that it's something other than the sample, right? You cannot really know the population value from the sample, right? So that means you have to have some information outside the sample somehow. So for example, in the toy example, in this toy example, maybe x is acre, right? X is acre and y is yield. So acre probably know from the list or from acre doesn't change over years, so we know that. But the yield, crop yield may change over year by year. So that's it makes sense that you measure yield from the sample, but acres you can treat it as a known from external sources. Okay, so this is the ratio estimator. So ratio estimator for the total, this is the ratio estimator for the mean. So so you basically you have this. So you can see that this is right. The denominator is unbiased estimator of x. So approximately, right? So this will be if sample size is large, then this will convert it to x. So then this value will be close to one, right? But in the small sample, maybe it's not really equal to one. So anyway, this one basically has some adjustment. So first of all, so here's some algebraic properties. Linear in so this is so this if you write it x times oops, so you can write it as a what I equal to a 1 over pi I x divided by x hat Horowitz Thompson times yi, right? So Horowitz Thompson estimator is this one, and then you have this ratio to be applied. So that if you write this way, this is linear in y. This factor is random variable. And then what do I mean by that? Okay, let me use this example. So suppose so this is a kind of small uh, small data, sample size 20 from this distribution. Okay. So X and Y is roughly linearly correlated. And in this case, suppose my population mean of X is 5. So this is X bar N. So that means I generated a sample from a population, from a model with mean 5. Okay. But my sample, right? My sample have this 5.33. Should make sense, right? Even though I generated from, say, X is from normal 5 and 2 square, right? Suppose I generate this. But that does not necessarily mean that sample mean is equal to 5. No, right? Can be something close to 5, but can be it's not necessarily exactly equal to 5. So that means my sample actually sample mean is this is my sample mean. Okay. So what is difference tell you? Okay. That means my randomness, right? The random selection happen to select the samples with higher values of X than than the mean, right? So than the population. So in other words, at least so okay. So it's like this. Suppose this is my population, right? But by random chance, I happen to select bigger ones. And I know that, right? I know that my sample oversample the bigger X values. That means it's better downweight the sample, right? Because I know that they are large. So that is the basically idea. So that means you X bar N divided by X bar sample is what? 5 divided by 5.33. So that means I'm going to downweight. So that is basically what this is about. So this is the case, right? So here in this example, my Horowitz times estimator is greater than the population level total. So that means my ratio estimator will be smaller than Horowitz times estimator. Okay. And another interesting part is that if y is exactly equal to x, or even could be if y is kind of a c times x, then the ratio estimator equals to x. So that means my yi is equal to y. Perfect. Okay. No sampling error. It is a perfect. If this relationship is perfect relationship. Okay. Because of this. This one is true because we, you can check easily. right? Ruby Thompson. So the showing the proof is just algebra, simple algebra. The meaning is that even if I use only sample element, I recover. I can recover my population total, right? Which is nice. So that is later we'll see this property. We call this property is a calibration. Calibrate in the weighting. Probably you heard about the calibration weighting, right? I mean, so that is we want to benchmark. Sometimes we call benchmark. Benchmarking property. So this X is a benchmarking total, and my weight satisfies this benchmarking property. Okay. Now, so this is algebraic property, right? Algebraic property means that we don't really discuss bias, variance, this kind of thing. No, just the algebra, no random variable. Just you can put those who knows nothing about statistics can prove it as long as the person is familiar with this algebra, right? This is algebra. But now I'm going to talk about statistical property. So when I say statistical property means bias, variance estimation, asymptotic normality, and also all kind of things, right? So first thing you note is that ratio estimator is a nonlinear function of two random variables. So the random variables are, oops. Two random variables, right? Is two Hurwitz-Thompson estimators. Notice that R hat is estimating the ratio in the population level, right? Ratio of two totals in the population level. And then you can see that this, you can write it as X times the ratio. And ratio bias, so bias of ratio estimator is so important that it has a name. It's called ratio bias. So bias of R hat as an estimator for R. And then expectation of which is the expectation R minus R. And why ratio bias exists? Because this is equal to this by definition. And then this equality does not hold. You cannot really apply expectation numerator and denominator separately. No. Even if two random variables are independent. So if X and Y is independent, then Y divided by X, so independent, then all you can say is that this guy is Y times 1 over X. You can do that, right? But even this one is not equal to this. So we need to investigate the nature of this ratio bias. So the first result is that the ratio bias can be written as can be understood as the covariance of the R hat and X hat divided by X. So we'll approve it. So, but I will leave it for now, and then just discuss a little bit further. So then, MSE is a variance and bias, right? Bias square, variance on bias square, and then variance. Then you can write. So now question is, what I'm going to do is that the point is that I want to compare the magnitude of a bias to the magnitude of a variance. Okay, so I know. So why I'm doing this? One important weakness of ratio estimator is that it is bias estimator, right? So people may criticize ratio estimator because it is bias estimator, right? Why you use that, right? I mean, so people may kind of argue. And our defense, our answer is that, okay, suppose variance, the magnitude of bias, so this ratio, right? So magnitude of bias square over the variance is say less than 5%. Maybe it's okay, right? I mean, so then variance dominate. So that is a kind of a message. So end of the day, what I'm going to show is that this will go to 0 as and go to infinity. So I know bias exists, but asymptotically, variance also goes to 0. Bias goes to 0, but bias square goes faster to 0 than the order that variance goes to 0. That is the exactly key idea. Okay. So in other words, usually variance is 1 over n order. Bias of this ratio estimator will be also 1 over n order. And so that means bias square. So bias square divided by variance hat is O 1 over n square divided by O 1 over n. So that means goes to 0. Okay. So denominator goes to 0, numerator goes to 0, but the numerator goes faster than to 0 than the denominator. Then overall, right? Overall, it will be go to 0. That is the what I'm going to show. Okay. So I will show that, but now, so that's basically what, and then if that happens, that we can call it bias is negligible, right? If a bias divided by square root of the variance goes to 0, then we have two good news. The first good news is that if you consider central limit theorem, we have so this we can decompose two ways, right? And then the first part goes to normal 0, 1 by CLT. Second part is that it goes to 0 if bias is negligible. So and then by velocity we get. Okay, let's try to prove it. Okay, so we should to show bias R hat equal to minus covariance R hat X hat divided by X. By the way, this guy is expectation R minus R, which is expectation over Y hat divided by X hat minus Y divided by X. The right side is a expectation over R hat R X hat times expectation R hat expectation X hat divided by X minus. So which is expectation Y minus expectation R hat expectation which is minus Y given X plus expectation Y. So basically that is R expectation R hat minus R. So we proved. So this guy is equal to this guy. So basically the bias of ratio has some covariance interpretation. That's a basic message. Okay. And then that means relative bias. So let me back up. Bias R hat square is equal to, using this one, covariance R hat X hat square divided by X square, right? So that is correlation R hat X hat square times variance of R hat and variance of X hat divided by X square. So that means covariance is correlation is always right. So we get this because correlation is less than one, less than or equal to one. So we get that. You can get rid of this covariance correlation. And then you move this one to here. And so divide by variance. Which is, so relative bias of R hat is bias R hat divided by square variance of R hat, right? So this guy can go to the denominator to obtain this relationship. So this guy is sometimes called so coefficient of variance. P coefficient of variation for theta hat is variance of theta hat divided by expectation of theta hat square root. So that is the definition of the coefficient of variation. CV. Anyway, if n goes to infinity, right? If n goes to large, so then variance will goes to zero, right? So n goes to infinity. You may wonder, what's the point of allowing n goes to infinity for finite population sampling? Your finite population is finite. How can you increase your sample size, right? So that's could be a legitimate question. The answer is that we also allow the population size increase. So it's a kind of a concept. So you want to, but we want to apply some asymptotic theory. Then how can we define a finite population? Maybe you allow that as you increase your sample size, your finite population also increases asymptotic, same rate. So that is the idea. But without asymptotic theory, it's very hard to say anything, right? I mean, so ratio bias is negligible. So that is basically all about the property of ratio bias. So bias of ratio estimator. You may wonder, how come you just what is the so you may wonder, so what? So how does it connected with the property of ratio estimator? So ratio estimator, right? Y hat ratio estimator is x times r hat. And I only discuss the property of the ratio, not the ratio estimator. But interesting part is that ratio bias of r hat is a ratio bias of relative bias of r hat is a relative bias of y hat r. Why? Because the definition of relative bias is bias of r hat divided by square root of the variance, right? So that is the definition. Now, maybe I will use the next page. Okay. So what I just show, so what is the, we should to show that relative bias of r hat is equal to relative bias of x times r hat, right? Which is a ratio estimator, y hat r. So how to show that? Well, the right-hand side, bias of y hat r divided by square root of variance of y hat r. So that is the expected value of y hat r minus y divided by variance of, yeah. So okay. this is x times expectation of r hat minus r divided by variance of x square variance of r. So that actually has a cancellation. So that is relative bias of r hat. So that means showing this property is enough, right? Same as showing the property of the ratio estimation. Okay. So that's all about bias of ratio. Variance is actually easier because we already discussed the Taylor expansion, right? But I think this is good for today. So we'll continue this Thursday. Okay.